In this lesson, we will be looking at balancing chemical reactions. When chemical compounds begin reacting together, they can be written with symbols to represent the products and the reactants. This allows scientists to accurately communicate what chemicals are involved, how they're arranged. We can determine the amount of the reactants that are needed, as well as determining how much of each product is formed. All these chemical reactions must follow the law of conservation of mass. The law of conservation of mass states that in any chemical reaction, the matter, or atoms, can never be created nor destroyed. Therefore, the number of atoms and the mass of the reactants must be the same as the number of atoms and the mass of the products. Let's look at this equation as an example. Magnesium here is being added to oxygen. This is a straightforward synthesis reaction, and it produces what we would call magnesium oxide. Now, the way this equation is written, it is written as what we would call a skeleton equation, whereby it shows the reactants and the products and how they come together. What we want to be able to show is what we call a balanced chemical equation. And a balanced chemical equation also shows the ratios or the quantities for each of the reactants and products. When we say balancing equations, we mean that chemical equations that describe the reaction have to be balanced. In other words, there must be the same number of atoms on the reactant side as there are on the product side to ensure that no atoms are created or lost during the reaction. That is the law of conservation of mass. To do this, coefficients are used. A coefficient is a number placed in front of a compound, which makes every atom in the formula multiply by that number. So let's talk about some guidelines here before we get started. Number one, identify each of the elements that are present and the number of atoms in both the reactants and the products. Number two, balance what we call polyatomic ions first as a unit. We'll talk about this more in a moment. Number three, balance all other atoms one at a time. And I would leave hydrogen, H, and oxygen, O, until the end. Number four, check your answer. Your coefficients should always be in the lowest terms possible, so you may need to reduce them. But check your answer, and you'll know if you got it right. On the back of your periodic table and in your textbook, you'll see a chart here which we call our polyatomic ion chart. This chart shows groups of atoms that often travel in groups or in pairs. Poly meaning many. So some that you might be familiar with, you might have heard of things like nitrate. Nitrate is a nitrogen and 3 oxygens that travel as a group. You might have heard of something like a sulfate. A sulfate is when you have a sulfur and an oxygen. There's 4 oxygens, and they travel as a group. So anytime you see these groups of ions, we can consider balancing them as one unit. So let's try our first example. Here we have H2 hydrogen plus O2 oxygen, forming H2O or water. From what we've learned already, we already know that this is a synthesis reaction. This is what we call, again, a skeleton equation. We want to balance it. And so as we balance it, we're going to look at the number of hydrogen and oxygens on both the reactants and product side. So for the reactant side, we can see here that we have 2 hydrogen atoms and we have 2 oxygen atoms. On the product side, so after the arrow, we also have H2O. We have 2 hydrogen atoms. Our problem here is that we only have 1 oxygen atom. So what we need to do is add coefficients to balance this, to follow the law of conservation of mass. To do this, we add the coefficients. We just kind of start one at a time. Well, to balance our oxygens, I need to add a coefficient in front of H2O. If I add a coefficient, that multiplies my H2O, and it now gives me 2 oxygen atoms. It also multiplies and said, well, I have 2 of everything here. So not only do I have 2 oxygen atoms, but I have 4 hydrogen atoms now. Looking at this, we can also now have to go over to the reactant side, and we have to make sure that the reactants equal the products. So I only have 2 hydrogen atoms in my reactant side. I'm going to need to add a 2 in front of that H2. Again, we can't change these small numbers. We can't change how they're packaged, but we can add a coefficient in front of it. By doing that, I now have 4 hydrogen atoms. As a way to double check, you can go back over each element and say, okay, I have 4 hydrogen atoms in my reactants, and I have 4 as my products. I have 2 oxygen atoms in my reactants, and I have 2 oxygen in my products. And so I know now this is a balanced chemical equation. Let's take a look at example number 2. In example number 2, we have Ca calcium plus HCl is going to produce CaCl2 plus H2. Okay. Now we can look at this, and from what we've learned already, we should be able to identify that this is actually a single displacement reaction, and we see our products have been formed. That's a good skeleton equation. But to have a balanced chemical equation, we need to make sure that what we have on the left-hand side, our reactants, is going to be equal to what we have on the right-hand side, our products. So one of the strategies that you can use in identifying each element is writing down at the beginning how much you have. Well, on the left-hand side, I have Ca, and I only have 1 atom. I have H, and I have 1 atom, and I have Cl, and I have 1 atom. Every time you see a capital letter, it's a new element. Well, on the right-hand side, I have Ca, and I have 1 atom. But now you can see here, if I write these down, I have H, and I have 2 atoms. I have Cl, and I have 2 atoms. So I have Cas, I have calcium, I have hydrogen, I have chlorine, but I have different amounts. And so we need to go ahead and try to balance those. And to do that, we're going to add some coefficients. So one of the ways that I can do it, if I have 2 Cls in my product side, I need to have 2 Cls in my reactant side. So I'm going to go ahead and I'm going to add a coefficient in front of HCl. So let's go check and see how that affects our results. I still have 1 Ca and I have 1 Ca. So that's balanced. But I now have 2 hydrogens, and so that is now balanced. That coefficient not only multiplies the H's, but it multiplies my Cl's, and so now I have 2 Cl's, and in my products I have 2 Cl's. So this is a balanced chemical equation, and it's showing that for every 1 Ca that I have, I actually need 2 units or 2 packages of HCl for this reaction to occur. Here we go with example number 3. And if you're comfortable with this, maybe you want to pause the video right now and see if you can balance it yourself. If not, follow along with me. Again, one of the strategies you can use is identify what do you have on the left-hand side and what do you have on the right-hand side. This will help you just write down and clarify each element. So on the left-hand side, I have Al and I have Cl. Well, I have 1 Al, 1 aluminum, and I have 2 Cl's. I have 2 chlorines. We can see this synthesis reaction has produced AlCl3. And so what that's saying is I have 1 aluminum, but I have 3 Cl's. And this creates a bit of a problem for us because my Cl's aren't balanced. Now, one of the little tips that you can try to do, if you have a 2 and 3, which is fairly common, you want to try to get them to be a multiple of 6. Okay? And so on the left-hand side, if I look at Cl2, I say, well, I need it to balance on the other side. I can multiply it. What do I need to multiply to get to 6? And so I'm going to add a coefficient of 3. By adding a coefficient of 3, 3 times 2, I now have 6 chlorines. And so I need to have 6 on the other side. And so when I look at AlCl3, to get 6 chlorines, I need to multiply that by 2. So multiplying that by 2, it will give me 6 chlorines. But I have to go back and check, because by adding the 2 there, I now have 2 aluminums. And so I have to account for that. Those 2 aluminums, it means I'm going to have to go back to my left-hand side and add a 2 in front of that Al. And that'll give me 2. As always, go back and check to make sure that each is balanced. You have the same number of atoms as the reactants, as the same number of atoms as the products. So I have 2 aluminums and I have 6 chlorines. It is now balanced. Here's our last example. And again, if you want to go ahead and pause the video, try it yourself, you can do that, and then catch up with us when you're finished. This equation, it looks like a bit of a mess. There's a lot of symbols here. But again, we can recognize this as a double displacement reaction, which we've learned about those types of reactions already. And again, use the same strategies that we've been using before. So I would encourage you, as you get started, to write down what do you have on the left-hand side and what do you have on the right-hand side. So on the left-hand side, if we start writing these out, I have 1 Ca. One of the tips and guidelines I would encourage you to go by, these polyatomic groups, so when you see multiple ions, I have an S, an O, and a 4, that's a polyatomic. And so I'm going to consider that as one group. That SO4 is one group. So I have 1 of that. It'll just make your life a little bit easier. I also have 1 Al, and I have 3 Brs. On the right-hand side, or my product side, I can do the same thing. I have 1 Ca, I have 2 Brs, I have 2 Als, and now this polyatomic, this SO4, I have 3 of those. This can be a bit tricky when you take a look at this, but the SO4, when it's in brackets, I have 1 of those groups, and the number here outside the bracket, it multiplies everything that was in front of that bracket. So I have 3 of that group. Similar to if I put Al, that 2 is saying I have 2 of whatever was right before it. I have 2 aluminums. So now we're ready to go ahead and start to balance this so we have a balanced chemical equation. Well, it doesn't really matter where we start, but let's start with the polyatomics because that was part of our guideline. So I have 3 in my product side, and I only have 1 in my reactant side. So I'm going to go ahead and I'm going to put a 3 there. So that gives me 3 SO4s. So that's good, that's balanced. But by adding that 3, I now have 3 CAs. So if I have 3 CAs over here, I need to come back over to this side and I need to balance those CAs, balance those calciums. So to do that, again, I can add a coefficient in front. I'm going to add a 3 there. And so now I have 3 CAs. Always double check to see how that changes things. So by adding a 3 there, I have 3 CAs, and I now have 6 Brs. So we have to make sure we balance the Brs. I have 6 of those. Looking at the left-hand side, I only had 3 to start with, and so to get to 6, I'm going to need to multiply or add a coefficient here of 2. And so we're just going to go back and forth and add these coefficients. Well, that gives me my 6 Brs, my 6 bromines, but it also gives me 2 aluminums. When I look back on my product side, and I see I already have 2 aluminums. So go back and forth balancing these, and then when you get to the end, double check and see if you got it right. I have 3 CAs, 3 CAs. I have 3 SO4s, I got 3 SO4s. I got 2 ALs, I got 2 ALs, and I have 6 Brs and 6 Brs. This is now a balanced chemical equation. Again, these balanced chemical equations help us to see the ratios of how much reactant we need and how much product will be formed. And it allows chemists to do this instead of writing out long paragraphs. At this point, you should be able to go ahead and try the worksheet that we have for you. Identify the reactions that we looked at the other day, and now following the law of conservation of mass, you should be able to balance these equations to show that the number of atoms that you start with is equal to the number of atoms that we finish with. Good luck.